So now we're gonna go a little farther. I'm gonna start computing corrections to the picture that we computed thus far, that we have calculated thus far. So remember what the problem that we tried to solve. The theory is actually more generic, so in principle it doesn't have to apply necessarily to a binary system, and we will see how we can generalize many of the aspects, but we'll concentrate mostly on this problem. We have two compact objects separated by a distance r, the typical size of the order gm. This is the mass of each body. And they're moving non-relativistically, the relative velocity. And therefore, they emit gravitational waves. And the wavelength is much longer than the separation, which is much bigger than r. And what we did so far is do a multiple expansion here in r over lambda, which happens to be v, which is much less than 1. And a leading order, we computed the flux in gravitational waves, which is carried by the wave, so it's lost by the system. It's minus g Newton 5, QHA, and 3 derivatives, and here we put trace free. And since this is a periodic system, and we're going to work in the adiabatic approximation in which we calculate this in circular orbit on circular orbit, because we have an adiabatic parameter, remember, which is small. In fact, we computed this at leading order. This is proportional to v to the phi, which is very small. And therefore, in a period, there is a total power, so we can average over a period, assuming that the motion is circular at each order, which is what we did, right? So we did not really track what the instantaneous radiation reaction force is. And in fact, that's an interesting problem that I'll touch upon maybe later, how to calculate that, okay? Because there could be a lot of transients that average out that you're going to miss when you take this adiabatic approximation and you average over a period, okay? So this we calculated, which is the leading order. And there was another leading order here, which is, who is this Q? Remember who this Q was? This Qij was an integral on the volume. And remember, in this case that we studied at the end as an example, we had two localized sources, 2-point particles. So it just become a sum. But in general, it's an integral on space-time. And we concentrated here, we did the approximation. This was just a matter, just m, right? M delta, and then we sum. So if we put a leading order here, this is nothing but raw matter. So not only we have a leading order in the multiple expansion, we also had a leading order in the multiple moment, okay? And what I mean by that is that here, this object here can be corrected, can have post-Newtonian corrections. Not this guy, but this was the leading order, so if it's not leading order, the T00 itself. And in the multiple expansion itself, there will be also corrections that will modify what this Q is. So it will be plus ... because higher moments will also contribute to the Q. And each one of those will also have post-Newtonian corrections. Okay? So you see how this starts getting complicated. And now all these to compute the flux. But then to actually compute how the dynamics of the system, how it shrunk, how we computed this, what did we do? Well, we equated this to the loss of energy. And how do we calculate the energy? We just went back to Newton, right? So this was our leading order in the multiple expansion, raw matter leading order in the multiple moment, and in the energy, we also computed the leading order energy. That I think I called it R last time, this distance, right? But now I just call it back R, and I call R the distance to the source for the H, so don't get confused. This is part of understanding what the scales are and not get lost in nomenclatures, okay? So we use this. We did not derive this. I mean, you know this from Newton, classical physics. But obviously, this is not the end of the story. So there are also corrections here. And there are two kinds of post-Newtonian corrections here. There are corrections because, well, there are velocity corrections, obviously, because these are relativistic, special relativistic corrections even, right, that will correct what we mean by the energy, right? Like 1/2 mv squared plus v to the 4 plus blah, 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 the square root of 1 minus v squared. And there are nonlinearities. So the interaction here in GR is nonlinear, and the nonlinearities are parameterized by this ratio, Gm over R, which is also of the order of v squared, and that's why these are post-Newtonian corrections, okay? There are v corrections, and there are Gm over R corrections, but they all come out as factors of v. And those two enter here, okay? So then you see how it starts getting complicated, and then there is another type of corrections, which is what about the size? What about tidal deformation? What about the energy that it costs you to deform this object that can also back react in the orbit? What about the time dependence, oscillation of the quadrupole of the object itself that can also emit gravitational waves? And this could be even Newtonian, right? It doesn't have to be GR. In fact, there is a very strong Newtonian piece here with the neutron star that is important, okay? So how are we going to parameterize those? Well, we're going to say that the objects are compact, and therefore there will be also a multiple expansion, the same way that we did this multiple expansion. There will be a multiple expansion here in the size of the object, okay? So the same way that we do R over lambda, lambda is the perturbation of the system that has a quadrupole. R is the perturbation of the system that has a quadrupole. So we're going to do the exact same theory, except that it will be for the compact object itself, whereas this theory is for the binary. But formally, it's gravity coupled to an extended object, either a compact object or a binary. So we will end up with things which are very similar to what we have done. Okay? And the expansion parameter for that multiple expansion will be the ratio of scales, so it will be R over R, which is equal to Gm, M over R, that's R over Gm. So this is a new parameter. This is V squared. This is a new parameter. And now something interesting starts to happen. So everything we can compute in gravity, pure gravity, coupled to some T mu for the matter, say. But everything that happens at scales larger, my infrared physics, right? This is my UV physics, this is my infrared physics. Everything that happens at a scale larger than the size, right? It's all pure GR, vacuum pure GR. So the ratio of scales, lambda over R, Gm over R, is something that I can compute just in pure GR. I should be able, at least, and I'll tell you how. Now, where does the new physics come in? Where does the distinction between a black hole, a neutron star, or any other weird compact object comes in? Where does the fact that maybe there are new states of nature out there that we haven't seen yet? Well, they have to come from this number, from this parameter. This is the only way you learn about the UV physics. It scales like this, right? This guy will depend on some internal degrees of freedom or whatever. This will be our UV physics. And if you're an effective field theorist, what you do is, well, you start constructing effective descriptions in which you look at one scale at a time, and the effects of the UV scale on the infrared scale is treated as a series of Wilson coefficients, which for us will be a bunch of multiple moments. Okay? And those multiples depend on the UV theory. We already saw that here. How? Well, who is T00? T00 is mass times distance twice, right? Mx1, x1. This M of the binary of the object is the UV. It's information that you don't have here unless I tell you who this Q is. This was completely generic. I could have derived this and stop here and not tell you anything who this T00 is. This is completely generic about a compact in the sense that it's a compact support object that is emitting gravitational waves. This applies a leading order in the multiple expansion for anything. Now let's open the system. Let's look at the UV. What is the UV scale? Here. Where is R in this expression? There is no R anywhere. This expression depends on omega to the 6th. Only knows about the infrared physics. Only knows about lambda. Where does the UV physics comes? It comes when I open this up and I write the quadruple as mu, now R, right? Squared. UV parameter. Okay, and now I start reading off the physics of that UV parameter. Okay, so as often, this is the idea of decoupling, right? The long distance degrees of freedom determine how this dynamics is going to look like, how you're going to write this effective theory. All the UV physics will be in the Wilson coefficient, like how the mass of the W is inside G Fermi. Okay, so the same is going to happen here, one scale at a time. We will not know about MW until we really hit that scale. Or somebody gives you the electroweak theory and you do a matching. Okay, so we're going to have to do both. Either we match, because we do know what the R scale is. It's GR. So we can open this up. We actually did it. We open it up. I gave you this, which is generic, and then I open it up for you. I told you this is raw matter, and I calculate MXX, and I give you your Wilson coefficient. This is my UV parameter. It's the UV parameter of the long distance gravitational wave radiation zone. Okay? I have to do the same for this other scale. But I might not know exactly what this is. So we have to parameterize it in a way that maybe observations will tell us. Rather than matching to a theory that I know, I'm going to write that coefficient, tell you how the waveform is going to look like, match the data, and try to read off what the number is. Okay? And this number is key to see as a new parameter what is the new physics. For example, is it a black hole or a Newton star? Is it a boson star? Is there an axion cloud? It will all come from this parameter. Unfortunately, gravity is derivatively coupled because of the equivalence principle. As we will see, there will be many factors of this guy in front. Even though there will be enhancement by this number, there will be a GM over R to a very high power in the effects of the internal structure. The same way that happened here, right? We get too many derivatives, which is, this is, again, also the equivalence principle, remember? The Q coupled to two derivatives, to curvature. It cannot couple to the H, right? The mass is conserved. We cannot couple to the dipole. The center of mass doesn't move. It has to couple to the multiple, to the quadruple. Two derivatives. Ouch. Too many. Because too many of these guys, which will be too many derivatives, will cost you many powers of B. And in fact, it turns out that this parameter, even though it will enter in the dynamics to a high power, to the fourth power actually, it will be suppressed by a factor of V to the 10 over 5 pm. You will see why. Okay? So you really need very high accurate waveforms up to this order, which we don't have at the moment, to really read off this parameter that knows about whether you have a black hole or a Newton star. Okay? So what I'm going to do now for you is extend this that we already did. We already started doing effective field theory. we're just going to go further and see how we incorporate all the corrections. Okay? By the way, you might ask, if we don't have accurate waveforms to really tell whether it's a black hole or a neutron star, how do we know that we saw a neutron star? Does everybody know the answer? From? From light, so there is a counterpart, okay? But the LIGO papers are very careful to tell you that from the gravitational wave signal alone, they cannot tell, okay? Of course, you can try to model this. How? Well, unfortunately, we don't have much time to go through that, but you can try to say, if I know very well my waveforms up to this order, I can read off this parameter. Okay, it's very hard to do, but I can write numerical relativity codes. And I can try to get out from the numerical relativity codes how the pure GR dynamics looks like up to this order. And then try to cook up what this parameter looks like just by matching to waveforms in the numerical GR template bank, okay? But that depends on what masses you can run, whether you ignore spin or not, and what happens with these parameters, for example, with this parameter that we're going to use to describe the physics of the compact object, what happens for black holes, because that's what the numerical GRs people do. So we had to tell you what is the background value for the black holes that I need to subtract. And this will be one of the most mysterious things that I have found in gravity so far, is that this parameter is 0, the first guy. There are corrections, but the first guy, the first effect of the tidal disruption of an object for black hole is 0. There is no tidal disruption for a black hole, which is super remarkable, because if you put a star in a gravitational field, it will definitely squash. Black holes don't want to, okay? Okay, very good. So what we're going to do now is construct this effective field theory approach. To gravity. Which will allow us to calculate the corrections here, the corrections to each one of these guys in Pn, the corrections in the multiple expansion, the corrections of each one of them in the Pn expansion, and the corrections from all the scales to the binding energy. Okay? Oh, maybe I should just say one more thing. And why this is useful? Well, we will describe the system very well, but also because this will be one way in which we can compute this parameter, right? Because if you have the flux, that's how we did it, by the way, right? We put E dot and we put this in here, right? And we use the Kepler law to relate R to omega, and then omega dot was related to this, which is also omega, and we solve for omega, okay? So we can do exactly the same thing once we have the full answer in the post-Newtonian expansion. Okay, and if we had this guy omega as a function of time or as a function of frequency, remember we can go to Fourier space. Then if you integrate omega, and remember there's a factor of 2 difference between that and the frequency of the gravitational wave, between the initial time it enters the detector and the final time. So this is the phase. And this is what we want to, well, it doesn't matter. You can put some initial phase at which the gravitation will enter. And this is what we want to observe. And remember that you can look at the data and then you see the waveform, right? Or you see also, for example, how much the frequency changed, and that's how we calculated, for example, the shear mass and so on, okay? Then from here we can do that analysis. So if we know how this varies with time, which means if we calculate this parameter, which is this equal the dot of that, then we're in business. Okay? Okay. Now, I don't remember. Okay, so this was originally introduced in this paper, the main ideas. FTH 0409156 by Goldberger and Rothstein. And my thesis was to do the spin case, so as GR, so this is not spin, which is mostly what I will tell you about. And all the phenomenologically interesting part, which was new at the time that I computed, I will not tell you much. I don't have time, unfortunately. But ask me later. Why write this? Well, credit when credit is due. This was originally introduced by Walter and Ira. 11. But one thing, and I wrote a review. Physics report. We've been recorded, but Marco is not here. About Elsevier, I'm sorry. So this is 16.01.04.914. But if you look at the published version, my paper was published in PRD in May of 2006, and the number is 104031. This paper that was written a year before was published in 104030. It's the previous paper. Okay? We're basically back to back. And the reason is because the community was very resistant to these ideas I'm going to tell you about. And now almost everybody is using it. So don't be afraid if you submit a paper and it takes a year to be published, because eventually you will take over. And now there are even new ideas of people using the amplitude technology that you heard about and you hear from Nima. They're also taking these ideas to the next level. Okay? But the community is not as resistant anymore. Even though, I don't know how many of you follow the literature and who is prominent in this business of computing high accuracy waveforms, there is some dispute about the validity of some recent results. So we're still discussing these issues quite a bit. Okay. So let me just make a picture that will be more instructive. So we have in length, we have R, and we have lambda. In momenta, it will be 1 over R, 1 over R, 1 over lambda, right? So this will be my UV, my IR, okay? Now the ratio of scales is V squared up to this parameter, R over GM, that we'll get back to, and this is V. So they are separated. Now here, we have a theory of some compact object at the scale R, right? Which has some T mu nu. And it's coupled to, I'm not going to change gravity, okay? So Einstein gravity. Now, if we look at the object from far away, and by far away means that at scales of the order of R or lambda, right? Then we can construct an effective theory in which we treat this in space and time, right? As a point particle. So it will be a theory of a wall line coupled to long distance. And by long, I mean longer than the scale R, gravity. And the light degrees of freedom are translations and rotations, so this guy can be somewhere and can also rotate. And that rotation can be described, for example, if you put a basis there that moves with the body, right? So it's essentially a theory of point-like objects coupled to long-distance gravity, which means that we're going to take Einstein gravity. We're going to be always in the weak gravity regime for long distance, but in principle it doesn't. Here it could be strongly coupled. We don't care. What I mean is that this theory I'm going to write in here, which is at scales in which the post-Newtonian expansion works, so there's a clear separation of scales here. This is weak. So these are long-distance gravitational fields, longer than r, and longer by later, right? Here we are not yet in a binary. This just means I'm probing an object with a long-distance wave. It means eventually it will be probed by the companion, which is in a distance r, right? But this just means that variations of this field, right, are much longer, vary on much longer scales than the size of the object. So if this is the typical, let's call it lambda twillo, not to confuse with this lambda, it means that derivatives of this field are of the order of lambda twiddle. Okay? Sorry. Long. I'm telling you all this because this is much more generic. This same theory will apply also here for the binary. Okay? So that's the trick. The trick is it's always, that's why it's called, the original paper was effective zero approach for extended objects, right, in gravity. So you have an extended object and you probe it with an external long wavelength field, you can write this theory. And you can do this here, you can do this here, you can do this in any case, in which there is a separation of scales. Okay? In fact, we're going to write exactly the same theory here, except that the coefficients will be different, but the long-distance theory will be identical. Because it's a long-distance gravitational field coupled to an extended object, be the compact object, be the neutron star, the binary system, with neutron stars, with black holes, with whatever. Okay? Now, what did I call it tilde here is because the variation of the long-distance field, we have two components. Either there will be binding forces or there will be on-shell modes. Right? So they will vary in different scales. This guy will be further decomposed into the two relevant scales in the problem, which we call potentials and radiation. So sometimes this guy will vary on the scales of r, and sometimes it will vary on the scale of lambda. But they are for sure much longer than the size. Okay? But these potentials and radiation only comes into the game once I put this guy in the field of a companion. There is no potential if you're shining gravitational waves to a black hole. But you can still write the same theory. Okay? For example, if you're going to compute the cross-section of gravitational wave scattering of a compact object in the limit in which the frequency, in the limit, imagine this theory would be equivalent to say you shine some gravitational waves in a compact object. If this frequency, the gravitational wavelength is longer than r, so omega r is much less than 1, then you can write exactly the same theory. You have a point object interacting with long wavelength fields. It's exactly the same. And this is now on-shell scattering. Okay? That has nothing to do with the force, which is completely, almost at least in order, is static. It's a tidal disruption. It's the same theory. This is why it's so beautiful, this effective zero formalism. It doesn't matter. You can be on-shell, you can be off-shell. In fact, we can use this to read off the coefficients and then put it here and know how this is going to disrupt in the presence of a companion. Once we know how it responds to an external perturbation of any kind, as long as it's gravity, of course. Okay? So that's why effective zero is good for. It's universal. The universality is part of the whole business. Okay. And I'm emphasizing this over and over because the same theory we write here is the same theory we're going to write here. It's just that the multiples here and the multiples here will be different. One will be the object, the other one will be the binary. Okay. But once you do it once, and you do it once for all. Any theory. Okay. And in fact, recently, very recently, Walter and Ira put up a paper in which they do basically the same theory I'm going to describe for you in the quantum regime to see how Hawking radiation could alter this picture. Okay? So you see how powerful these tools are. Very good. So now these potentials and radiation will be for the case of the binary, and we'll see how that enters. Unfortunately, I don't have much time to justify what this means more formally, which is associated with what is called as the method of regions. So usually when when you do an effective theory, you say, okay, there's new degrees of freedom. For example, how many? 10 to the 40 protons, neutrons, not protons, sorry, neutrons in the neutron star. Imagine trying to solve the dynamics of all those to know how the waveforms behave, right? All the constituents of the neutron star, all the binding energies between all the objects and so on. Imagine if you had to know that, to know precisely how the waveforms look like. It would be impossible. But we don't care. We integrate those out, right? Point particle. We have to put that information somehow, and it will be in those coefficients. Okay? That would be the trick. That's why it's so powerful. But you're used to integrate out real degrees of freedom in the sense that there are new degrees of freedom, forces, QCD, everything out, and then just gravity. You're not used to, in general, to take one field, decompose it in modes, and integrate out one of the modes, and keep the other mode. That's what this potential and radiation means. It's the same long-distance field, but sometimes it will be the binding off shell, sometimes it will be the radiation. Because the binding happens on length is important. There is no decoupling time, but in space. Length is much shorter than the scale of lambda, the radiation, which is on shell. Then we can integrate out those potentials. So here, there are two point-like objects. Here there is one. I have not put it yet anywhere. Now we put them in a binary. Now we have two. Now the scale R appears because there is a companion. We have two. Now we have these potentials that bind this together. Here, we're going to have one again. But this guy now is going to be the binary. So we're going to, here we integrate out the scale R, point particle. No more R, it's a point. We're going to write an effective theory that knows about this through these Wilson coefficients. Here, there are two particles binding. Integrate out that scale. 1 point. There is no more scale R anymore. The scale R is UV, it's gone. There's only scale lambda. We're going to write the same theory. Exactly the same. Long distance now will be binary as a point-like. Long distance now will be just plus only radiation. So we integrate out the potentials that live here, and here we only keep the radiation mode, only the infrared. So we have to tell you how to get rid of those modes.
Can you really do that when you're trying to compute post-Newtonian connections?
That's exactly what we do to get the post-Newtonian corrections. Because this theory, this binary, this point-like particle, you do this here without even thinking. Forget about this. Just look at the neutron star. Which theory you know of a point-like object? So what is the action for a point particle? A leading order, like no structure other than, what is the first thing that appears? Louder. Yes? Yeah? Sorry? Yes, what is the first action? What is the action of a point particle in GR or special relativity? It's md tau, right? And this is the square root of g mu, v nu, and d sigma, right? Look, I don't want to get too fancy, right? This is something that you know, it's just maybe you never thought about it this way. And then you can try to do it better and generalize it and make it more consistent. I mean, effective theory is just educated multiple expansion dimensional analysis, okay? You just have to know what you're doing, identify your right degrees of freedom. This method of regions, as you will see, is actually quite subtle. but intuitively it makes perfect sense. And by the way, in gravity, for those of you who do QCD, there are only two regions. In effective theories like soft collinear effective theory and NRQCD, I mean, there's much more to deal with, right? And there are quantum there. We don't have the soft modes here. This will be like potentials, what we call ultra soft. They are not soft because it will kick you offshore. You cannot be offshore, classically. So there is a whole literature in particle physics and QCD that deals with this formally, okay? I'm going to do it classically, and I'm going to do it in a way that I don't need the other things, even though I'm motivated by the other things, because Ira in particular is a QCD person, NRQCD or HQT person. But what I'm going to say here is like we have done it all the time without thinking. When we write this action, in your special relativity class, you put eta here, right? Who's M? Say, take a neutron star. Who's M? Is M the sum of the masses of all the particles? Yes or no? We're not so sure what we're doing. Eh? There is binding, okay? So this is the binding energy, or the binding mass of the neutron star. You cannot like rip it apart unless you do something. It's not the sum of all the masses. There's a lot of UV physics hidden in here. Potentials, forces, quantum mechanics, everything is in there. This M, well, we're going to get it from gravitational waves. But imagine if you could calculate it, you could actually get what this M is. In fact, there are bounds on how big they can get, which is 3 something solar mass. So we're going to do the same for the binary. Why it's so mysterious? The binary has a binding energy. That binding energy knows about the forces. It's not just the sum of M1 plus M2, period. But I can calculate it now. That's the whole thing. Because I know how to include these binding potentials. And that, I forgot who asked me, that's how we match for this guy. And matching for this guy here will give us the E, the corrections to the E. Because this will be like kinetic plus potential of the binary in this theory. So if I know how to match this M, which is my first Wilson coefficient, in the zero order multiple expansion, I'm done for the E. Okay? So I had to devise a way to match for this, which will be solved for all these potentials and put them back in the action, which we will do through Feynman diagrams, like in the usual way you do it in quantum mechanics, in quantum field theory, except that it will be all classical, meaning 3-level. You will see what I mean. Actually, okay. Tomorrow we'll see how we take the, if I have time, the classical limit of the actual quantum calculation, how the loops are playing a role. Okay. But if you have never seen quantum mechanics, you don't have to. It's all classical. You're trying to solve for some modes that you're going to plug it back, right? And you're going to try to read off of the effective theory where is your binding energy. And that's half. That's the energy that we need. Okay? So if we do all these steps and you read off some of the coefficients of your effective theory, you are almost there. Now we have to tell you what comes here. That would be the catch. That would be writing this theory, which incorporates the effect of the size in the pawn-like action. We already wrote part of this, or I already told you a little bit of this, and I'm going to do it more carefully now. If you were doing electromagnetism, say, and you have a charge phi and you're shining light, you will do the same. There will be a VA-QVA coupling, okay? And they will come, they will be responsible for the dipole. So if you look at this far away from, if you shine light, that its wavelength is much longer than the size, then you can polarize the sphere, and as you know, there's a coupling P dot E. And I already told you, I forgot if it was the first time or the second time, that in gravity what's going to happen is we're going to have to write something like Q dot E. And then we'll have to write more. So that's what we have to do. We have to get our intuition of electromagnetism and upgrade it here to gravity. And then try to think about who these Q's are by doing a matching. Now I just told you, if I match for M, which is the binding energy, I could get the energy. So if I match for a 1-point function, which is coupled here, for example, to the electric field, or here to the electric field, then I can read the dipole. If I can look far away to the electric field, I know it decays like P over RQ, I can read the dipole. So I can try to do the same here in the binary to try to read off the quadrupole. So there will be a matching. So I will write a theory which is generic. I know how the theory looks like from the long distance degrees of freedom, the metric field here, the electric field here. I don't know who these UV coefficients are, I need to match. And the matching occurs in this interface between the UV and IR. So same story, Pohn-like action, binary non-discovered action, only coupled to radiation. And this Pohn-like action will be a theory, binary as a Pohn-like plus multiples. I was counting on bigger boards, as you can see. Which we will write. We will write this explicitly, okay? Carefully in GR. And then we just have to read off those coefficients. Now, if I know who the Q is, which, by the way, will start like this, with T00XX, you will see how we get it. Now, completely independent of what we did before. And then I will tell you who the T00 is by matching. And the first term will be M, will be just the mass. Because the radiation could come just from motion at leading order, right? The T mu nu of the system is just M at leading order, okay? But that's not the whole story. There will be corrections from the binding energy and also relativistic corrections. So that's what we're going to do. And after we know the Wilson coefficients, but there is one more step if you want, but which is kind of implicit. So there is one more equation that we used to get that I didn't write. So we know the flux, we know the binding energy, but we also use the equation of motion. We use Kepler's law. Kepler's law gave us the R versus omega, right? Gm over RQ equals omega squared. So we need the equations of motion to be able to put these dots on top of this guy to know what the flux is. But those will come from the binding, because if we know the potential, we take derivatives of the potential, and then we get the forces, and that gives us accelerations, and that's what we need to complete the picture of taking dots. So we are not done with the flux and the binding, we still need to know how to take those dots. Those dots obey some equation of motion. But once we know the binding energy that derives from a potential that we're going to calculate, then we know how to take the dots. Okay? That will be the last step. How do we get the potentials that will come from the action, the effective action that we're going to calculate? All right. In fact, okay, no, let me just stop here. Any question? Does this make sense? Yes, to everybody? All right. So now we're going to construct the theory. So I don't know how familiar you are with all this effective field theory framework. What you do know is that if you have an action, just briefly, right? Because we're going to do this, so I'm saying I'm going to integrate out some degree of freedom. It means that, especially at the classical level, it just means let's solve for that in the field of the long perturbation and plug it back into the action. Okay? So you have a light field, and you have a heavy field, and you get rid of the heavy. This is light, and this is heavy. And you are working at energies, say, which are much less than the mass of the heavy guy. So then you write an effective theory, which only has the light fields, and the information about the heavy guy, heavy, comes from these coefficients, right? So they enter in the action. So there is the leading order part of the light field, and then you write everything that will depend on whatever dynamics of the heavy fields times some operators of the light field. And these are, as we heard maybe yesterday, some people discussing some of this. This is higher dimensional, higher derivatives. So they're suppressed. Well, sometimes we just say there is some Cantor scale. It's not always exactly M. It depends on what the physics is, if it's weakly coupled, strongly coupled, if there is a direct coupling, etc. So there will be some scale associated with this other sector. Okay? So those coefficients know about that scale. And this will happen to us as well. The coefficients, like M, knows about the short distance physics. Okay? So now we're going to do the same, but these light fields will be like the position of the center of mass and all the short distance motion of the particle. I don't care. So I'm just going to factor all that out. The rotation, right? And we're going to have extra terms that we have to parameterize. Okay? And we'll see how we do that. And the long distance leftover field is like all the short distance modes of gravity plus all the neutrons plus QCD is gone. And it will go into these coefficients. Okay? Very good. So now we're going to write that theory. So what is my effective theory? This theory of a point-like object coupled to long-distance gravity. Well, we already wrote the first term, m d tau. I can use any parameter that I want. I don't have to necessarily use the proper time. In fact, in a post-Newtonian expansion, it would be convenient to choose the coordinate time later. Of the background metric, right? Which we can synchronize. I think they're synchronized with our clocks. Right? Now there is a spin part, the rotation. So this is the center of mass. Sorry, I should say. I don't explicitly say, but we're looking at the long distance degrees of freedom, which is the bulk motion, right? We integrated out all the short distance degrees of freedom, which means all these displacements. So there's a center of mass, and all the displacements with respect to the center of mass, gone. I mean, that's our spherical cow, right? We do it all the time. We are effective field theorists by nature, maybe except string theorists, but we do it all the time, okay? We just don't stop to think about it. Here there is another Wilson coefficient. So this is translations. If you want, we are breaking translations and rotations. There are two Goldstone modes. So it's translations, there's one Goldstone mode associated with this guy, translations, right? And then rotations, which is spin. And this is, by the way, the Noether theorem. That's the only thing that when you compute the one-point function of the metric, you can depend on mass and spin. So here, it's a little more complicated, and there's a lot that goes into here that I'm not going to explain, because I don't have time. These are the Ricci coefficients. It doesn't matter if you know what they are, because we won't use them. And this is the spin tensor. So this is my Wilson coefficient. This is my Wilson coefficient. This is my CI. The metric is hidden here. The metric is here. These are the first terms, right? 0 derivative, 1 derivative, and now more derivatives. Okay? Plus dot dot dot. Now, what can we write with two derivatives? Well, what are the symmetries? In fact, if you think about what we have here, and by the way, this AV are associated. So, okay, this is just one comment. This frame moves with the particle. Now, at each point, you also have a frame in which you're free falling, in which the metric is flat. In that frame, this guy is rotating in space-time, so it's a rotation and a boost. So in that frame, this guy is like just a boost and a rotation. Okay, so it's like in the frame of the free falling that happens at every point, that is charting space-time. I have a rotation, an element of the Lorentz group, right, that describes the rotation with respect to that frame. And that's what this AB means, is the rotation with respect to that free-falling frame. It's all diff invariance, it's all fine, you just have to put these E's properly. So now we start having more coefficients. So what can we write that has two derivatives? Yes?
Just a question. Now that we're caring about scales.
The what?
Now that we're caring about scales and we're working with scales, I wonder, is it true that we can always write Gemini as eta plus h at every scale?
No, remember I told you what happens here, I don't care. There are short modes of the gravitational field and there are long modes of the gravitational field. My effective theory is of the long modes, in which I know by separation of scales that I just told you that I am in the weak field regime. That this scale r is much smaller by b squared than this scale. Okay, so I am looking on scales which are longer than the size. When those two guys get very close to each other, I cannot do anything. Now I'm writing a theory of the weak field. At the weak field level, I didn't write explicitly, but these are the long ones, in which I'm writing eta plus. But I already integrate out all the short distance modes that are here. All the gravitational modes on short scales give me the mass of the black hole. And that's a beautiful question, which is related to the discussion we had at the beginning. This M will be here even if it's just pure gravity. Why? Because it's built up by the short distance gravitational field degrees of freedom, which I integrated out. And that will give me the mass of the black hole. It will be built up by geometry on short scales. Far away, you know, you can expand the metric this way. Far away from the horizon, right?
We're at that scale where we can both see the compact object as a point like one, and
Yes.
the metric is a weak metric.
It's a weak metric because we're exploring that guy from far away. And now that's the discussion that we had. So what is the R mu of this theory? Oh, it has a localized, it has an M, it's M delta, right? The T mu, the T00. But I created that by integrating out all the short modes. By looking at Einstein's equation, well, G mu actually, long equal short, and then this I treat as point like. And match into a localized T mu that is proportional to a delta. So I created a black hole, even though it's not there as a T mu. Now, what can we write that has two derivatives? Well, we have a coefficient. Let's call it CR, for example. We can write, it has to be scalar, so my long distance symmetries, which I was saying, we have diffeomorphism invariance, of course. We have rotations of this frame, the local Lorentz invariance. So what can we write that has two derivatives? Well, we can play with the Riemann tensor. I just take contractions with everything that we have at hand. We cannot take with four velocity because it would be zero, but we can contract with this. Sorry, CV, this one is called CV, and then we can contract everything by itself. Actually, let's put the tau here to make it really, one more thing that we are using when we write this is reparameterization invariance, which allows us to choose any affine parameter. So here I put d tau, which means this guy goes here, which means this guy goes here, okay? And because this is parameterization invariant, then it's all good. And here, these velocities, sorry, let's call it differently because otherwise it wouldn't work. Let's call them u when they are u is dx mu d tau. If you want the other guys, you have to put 1 over square roots of this and so on. You can make it RPI invariant, representation invariant, just by putting sufficient square roots of GV square. Okay? Why we need that is so we can then later choose anyone, not necessarily the proper time. Okay? But I think someone said this already. I think the one working with Andy, right? You did. Yeah, exactly. This guy's gone. Why are they gone? Well, they're gone because this is my effective theory up to 2 derivatives, right? And I have assumed something. I will tell you what I assumed to write this. But if I look at plus the effective theory will be, I should have written here, Einstein-Hilbert with only the lone fields plus da 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 da. And that's how, by the way, I created in pure Einstein gravity this other part from the short fields in vacuum, okay? This will be vacuum Einstein for a black hole. A black hole will have spin and we have mass. But what happens is that if I vary my action and calculate the equations of motion, it's a localized source. This is localized on the wall line, right? So R mu nu equal T mu nu, or if you want, like G mu nu equal T mu nu, but the T mu nu is localized, so outside of the point is R mu nu equals 0, everywhere, except on top of the point, where it blows up, because delta of 0 is infinity. So what does that mean? That means that these guys cannot be physical. Either they are pure counter terms, or they are like quantum mechanical terms. How do I see that? Well, I see them this way. I'm going to do a field redefinition here. For example, look at this guy. So I do a field redefinition of my metric, degrees of freedom. So here, let's just keep G for now. It doesn't matter. Which is proportional to this coefficient and a localized delta. So we can write these guys as being somewhere So I'm integrating d tau. This depends on x. This is a field redefinition of my bulk action, so it has to depend on x. And it's proportional to the metric itself. Remember, we're going to compute observables. The observables will not depend on which coordinates, which metric fields we use. Sometimes this goes by the name of the equivalence theorem. So we can do field redefinitions. And if I do this field redefinition in the bulk action, then I get G mu nu delta G mu nu. This is proportional to the trace. So I'm going to generate an R that I'm going to put on the wall line. So by choosing, by choosing minus, I just immediately kill this term. Because all the traces I can kill this way. I can do the same with V's, and I kill this term. The trace or with V kills this term. 2 index tensors, no good. Now, there is something else I need to do. For those of you who have some knowledge of effective field theory, we cannot just vary the leading order term, we also have to vary these guys. We had to pull the field redefinition here. And the reason why you hear in effective field theory terms that vanish by the leading order equations of motion I can get rid of is a little subtle, because you still need to vary the subleading terms. What happens is that in effective field theory writes everything. And because you write everything, what you generate is already there. And therefore it just dresses your coefficient that you need to match anyway, so you don't care. So it's not that there is a completely innocuous, it just shifts your Wilson coefficients that are completely arbitrary until you match. And therefore the operator or the height measure is already there. And if it wasn't, and if you generated it this way, then you made a mistake and go back and put it on. But it's not completely innocuous because I did not write terms that goes like delta of x minus delta of x, but at different times. This is integrating time. So I did not put operators in which the two guys are on top of each other. These are like Darwin terms. If you remember the Darwin term in quantum mechanics. So you generate Darwin terms. So when the two guys are on top of each other, then those guys matter. So if we were doing quantum mechanics, actually these two guys will matter. And in fact, if you were doing a continuous effective theory, in which, for example, you follow cosmological perturbations, in which those guys can be on top of each other, then these terms do matter too. It's only because we are really far apart that we can ignore these guys. So we don't have them. So this is a bit of a subtle point. Subtle, not subtle. We live in the subtle because we're doing classical physics. So what we can write. Now I was cheating a little. Why was I cheating a little? I was cheating a little because I did not give you more to play with. I just gave you x and this frame for the rotation. But what about if the particle is not, say, spherically symmetric, if the body is not spherically symmetric? I'm missing that just by including those. So what if this guy has an intrinsic quadrupole? For example, a rotating black hole will have an intrinsic quadrupole. What happens is that it will be proportional to this S, because when the star rotates, or the black hole rotates, the shape changes and it induces a quadrupole, and that quadrupole is proportional to the square of the spin. But I should be able to write that operator here for any quadrupole. So how do I do that? Well, then I start adding these extra Wilson coefficients. And this ij are going to be associated with the space-like index in the rest frame. So this I goes between 0, 1, 2, 3. Now just look at 1, 2, 3. So this goes 1, 2, 3. And now we're going to look at the Riemann tensor. And we're going to take all the traces out. Traces go. Traces go. We just showed the traces don't contribute. So then we're going to write things in terms of, sometimes it's called C, sometimes it's called W, the Weyl tensor. This is the Weyl tensor, which is the same as Riemann, but you remove all the traces. Minus, delta, delta, r mu nu, and delta, 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 r, and so on. Right? All the traces gone. And this is nice because this guy can be decomposed in electric and magnetic pieces. For example, the electric is WVV. So you just sum in these two guys. So it's alpha, mu, beta, nu, mu, nu. Now, one thing which is nice about using the E and B, and this is with the epsilon WB. One thing that is nice about this is that it's traceless, so I cannot write anything as a function of the trace of E, which is r and r mu nu are gone. And it's orthogonal to the velocity, which is telling us that r mu nu, v mu, v nu was also 0. So I cannot contract with velocity, I cannot take traces. So I cannot write anything linear unless I couple to the spin, for example. So I can write E times S squared with two S's. I can contract. This is an antisymmetric tensor. This is a symmetric tensor. I cannot just put SE, gone. But S squared, SAB, SBC, AC works. And that's the quadrupole of a rotating black hole. So then you can write, for example, before writing this, let's write this guy. So there is an operator that I can write down that is proportional to the E coupled to the spin square. So in this frame, in this local frame, AC, is BC. And on units, if I do this, then this becomes dimensionless, and for a black hole, this is 1 for a black hole. It's not 1 for a black hole, for a neutron star. It's about 4, or between 4 and 10, I think. But this is very nice, because now we know how to include the effects of the rotation of a star in the dynamics. It's included in this operator. But it could be that the star that could have a very small spin, for example, neutron stars that merge within a Hubble time, the astrophysicists tell us that they don't spin very fast. So this effect is not very important. But the star could have a quadrupole moment, like tidal disruption, for example. How do we describe that? Well, we go to the rest frame. By the way, here these are 4 indices, these are 3 indices. I didn't tell you because it's a little tricky. So in the rest frame, what happens is that there is a 0 component of the spin. But this is 0 in the rest frame, so it doesn't contribute. But to do that in a Diffie-Hopkinson invariant way or Lorentz invariant way, it's a little tricky. So you have what is called spin supplementarity conditions, which is, for example, that S mu nu is equal to 0. That tells you that the 0 component is proportional to the velocity, but in the rest frame is 0. How do you put that in here is a little tricky. So I'm not going to go into that because I wrote a whole paper on that, on my entire thesis. But it's really the spatial part that matters. Okay. Here, the spatial part of this guy, and we're going to couple to E, which is projected on this basis. So if you want to put mu nu, you can put mu nu. I just had to put this E's to make a Diffie invariant, right? Do that as an exercise. And this is my Lagrangian. It's not the action. I had to integrate in detail still. Okay. But now I got then a new Wilson coefficient, which I can match. Well, the star has a quadrupole. Well, I read off the quadrupole by looking at the 1-point function. The 1-point function with decay, that's q to r to the 5th times xi xj. I read off the q and I put it here. But if I have a binary, that's also the quadrupole. And the same theory will also describe the binary. So we are doing the effective theory for everything at once, okay? For the star and for the binary. Now what's going to happen? Oh shit. What do I do? I'm going to start talking faster now, which is no good. So what's going to happen is the following. Who is this Qij? This Qij can have 2 components, right? It could have a part which is there already as expectation value on the short modes. It could be present there without any perturbation. The thing is rotating, it has a quadrupole. So if you take the expectation value on the short modes, which means we integrate out the short modes, right? Then there could be a quadrupole. It has to be the trace-free part, right? If you put a delta function, that goes away. But it can also happen, and this is the new thing, that this thing could respond to a long perturbation, to a long distance perturbation. But it still deforms on the scale of order r, so I can still treat that as a high-dimensional term. What do I mean by that? Well, you have seen this before. So this could have been, for example, the spin square term. This could be an example. Or if the star had a quadrupole to begin with. What is an example of this? You've seen this already in electromagnetism. Take a sphere, a charged sphere, which is neutral, but it has charge, internal charge, so the charge can redistribute and generate a dipole. So if you turn on an electric field and the pluses go up and the minus go down, you're polarized in an external field. And yet the sphere is still of the size r, and if this guy varies on long scales, in fact, if it's a constant, it doesn't vary, then this dipole, we know, it will respond to the external field with the susceptibility. This is the electromagnetic susceptibility. Now there is a gravitational susceptibility. It's the exact same thing. The masses will move in an external gravitational field. So we've seen this already. The quadrupole that will be generated, it will be there are so many notations for this guy. I'm gonna call it C for now, and it will be proportional to the field itself, omega. Remember, these are functions of time. But in the limit in which omega r is very small, I can Taylor expand this in omega r, and there's a first order coefficient in the static limit, right? Which is you turn on this field and you leave it there. In the zero limit, in the zero frequency limit, there is a real part. By the way, this could be real and imaginary because it could absorb as well. So this can have real or imaginary part, and this is absorption. And we can also determine absorption for black holes by keeping imaginary part. I'm not going to go into that, okay? But the real part at zero frequency is the usual susceptibility that we know. You turn electric field, constant, you leave it there, and this has a final dipole. But the same here, and this is called the tidal love number. And it's not called love because we like GR. It's called love because of some guy that was called H.S. Love in the 1700 or 1800, 1700. And I don't know what H.S. stands for. But this is Newtonian. Because if you go to Newton and the G00 is 1 plus 5 the potential, right? This is just two derivatives of the potential. This guy was just studying the obvious. What is the obvious? The obvious is that you can have a quadrupole that is proportional to two derivatives of the Newtonian potential. This is just the GR version. Okay? That proportionality constant sometimes is called lambda. Don't ask me why. So then we know how to include the tidal effects now in my effective theory. We know how to include the response, and we know how to include the intrinsic part. We got there, and then we write the operator. We can even replace it. We can put it back in the action, and we get something like this. And now I'm going to call it CE squared, because it's a square. And if we put the E back, you can show that this can also be written because it's Diffie invariant. There is nothing else, actually, which is just the same as this. That I could have written right away if the object is spherically symmetric in isolation. The only way it can get a quadrupole is as a response to the external field, so it has to start quadratic in the action because it's linear in the perturbation, right? And this you knew had to happen from Birkhoff theorem. Birkhoff theorem, also known as Gauss's law, will tell you that if you compute the one-point function in my effective theory, better be that just depends on the mass and the spin. If I had written something that depends on CR and CV, those two operators that I erased, then I would have had metrics that would depend, spherically symmetric metrics, which do not have any quadrupole moment. Say it's not rotating. So it's completely spherically symmetric, no axisymmetric in the case of spin. Say you have the mass and those two coefficients. It's spherically symmetric, it's static, and it will depend on the CR and CV numbers. That could not happen. So that we see why, right? But it could be that if you put a black hole in an external field, it could generate a love number. It could be that you take the black hole that it only has the M, you put it in an external field, and it responds to that background field by producing a quadrupole proportional to that background field. Are you following? Yeah? It turns out, and by the way, this is a derivative expansion. So what happens if I add more terms? Remember the decoupling in space? It's all fine, but time is different. Because we are localized in space, but how in time, the time scale of the changes. In this case, it's fine because we're just talking about the compact object. In the case of the binary, the time scale and the space is not the same because you go around and it costs you v. So there is no decoupling in time. So this derivative expansion in time, it just puts dots. It just means omega to some power, like omega squared, omega to the 4, and so on. Because we're looking at the real part, which is symmetric, omega goes to minus omega, so it's omega, it's 0, omega squared, omega 4. Those cost you 2 dots, so you're going to have e squared here, e mu nu, also e dot mu, and this is just dotted. It means derivative contracted with the velocity, so it's d alpha u alpha, right? If you want to do it gauge invariant, so it just means that there is a derivative in time expansion, okay? But now I'm going to do a little break because I see you're tired, and I'm not the first, and Jesse already probably did a lot. I'll give you 5 minutes in a second. If I put a background field, external gravitational field, and I look at the response, this would be my response. You would think you would generate something which is proportional to the background field, like we just determined here. So for a star, you get a love number. And in fact, you can power count just here. This is 2 derivatives. This is mass length squared. So you get mass length to the 4. Okay? And if this is compact, length if you want, if I put a G and I put a G, then this is like L. There will be, by the way, an L over GM extra parameter, which is exactly how this Wilson coefficient knows about this extra parameter. This CE squared knows exactly about the length scale associated with this new physics, I mean the neutron star or whatever it is. But I'm just going to tell you how it scales. It scales like length to the 5th over G. So if you have a star, you naively want to know how big this is. Boy, you scale with the length of the star, like the size of the star to the 5th power. And you can normalize it, divided by GM to the 5, say. And then you have a number. The star is a little bigger than the Schwarzschild radius. So you think naively that if you take a black hole, it will be order 1 in natural units, in GM units, right? It will scale like R Schwarzschild to the 5th, naively, right? Well, what happens is that for black holes, the standard number is 0. Take a star, it's not 0. You start shrinking until you get to the compactness of 2 GM. This guy vanishes. Now, as an effective field theorist, if you have an operator in your action that vanishes, that has a 0 matching coefficient, better be there is a symmetry or something that forbids it. Because what can happen will happen. I think Gelman said that it's compulsory. Okay? And it does happen for stars. Any star you can think of. It does not happen for black holes. Now, this does not mean that the black hole does not deform. If you put in an external field and you go close, and you look at the metric on the horizon, it's completely different. The metric is deformed. We are looking at a linear response, which means we're looking for very far away. How does the field decay as you look far away from the black hole in an external field? They will have a component that grows because there is an external metric, and they will have a decaying mode. That decaying mode will tell you what the quadrupole is. And if you do it for a star, it's all fine. You do it for a black hole, and when you put the matching coefficients at the horizon and you impose the regularity condition, something similar to in the hydrogen atom that gives you the discreteness of the levels, that you put that the wave function is regular, that regularity condition basically kills this guy. It cannot be there, because then it will blow up on the horizon. We have no idea if there is a deeper reason for this. And in fact, if you go away from 4, then this is not 0 anymore. So this is special of 4 dimensions. Also, we have no idea why. We don't know, by the way, we know perturbatively that it's true also for spin if you're spinning slow, but if you're spinning very fast, we also don't know whether it's 0 or not. So that's also something open. But now, and I'll give you 5 minutes. Now something very interesting happened. We have a way to tell by measuring this coefficient what is the equation state of a neutron star, because it will tell you how big it can get, because that's essentially how it scales. It scales with the size. Okay, so this depends on the equation state of a neutron star. If it's 0, then we are more confident that there's a black hole. But if it's not 0, and you measure the mass, you measure the first coefficient, the mass, and you get something bigger than 3 solar masses, which is what we know a neutron star can get, as big as. And then you go and measure this coefficient by doing high precision waveforms, which I'm going to show you in a second why this is 5 p.m. And you read it off. Like you look at the PDF of LIGO for this coefficient normalized by GM to the phi. So it's dimensionless now. And it peaks somewhere around, I think, 300. And if you don't include spin, the PDF of that parameter that they call lambda, which is a CE squared over m to the phi, and G equal 1 units, it peaks around 300. So there is a tidal deformability of the neutron star, ignoring the spin, because otherwise you have degeneracies. It doesn't want to be 0, it wants to be something. So we discover that there is some tidal deformability. Now what happens if you include the spin, then there is degeneracy, so you don't really know for sure. So you cannot really exclude the possibility there was a low mass black hole. But imagine you see now an object which is very heavy, 20 solar masses, and you do the PDF, you strike the waveforms really well, and it doesn't want to be 0. Then you go front page of the New York Times. You discover a new object in nature. Because this is an object that cannot be a neutron star, and it cannot be a black hole. So that's how we learn about new physics. Now, what can it be? If I have time tomorrow, I'll tell you about this gravitational collider. Or what can we do, and what can we explore with this, okay? So the last thing before we stop, why is it 5 p.m.? Well, now it's almost obvious, but this thing scales like m length to the 4, and if I put so it's this phi. If I put the GMs and normalize it, so I told you it was like length to the 4, length to the 5 over G, essentially. So if you put this guy, if you see the number of derivatives he has 4 derivatives. That's what this guy comes from. And if you compare with the GM over R of the Newtonian, then you get GM over R to the 4, and then divided by the other one with GM to the 5. So it's very easy to see that if you compare the two, there is a GM over R to the 5th relative between this operator. You just put the Newtonian potential for H, for the metric, which is GM over R. Take derivatives and compare with the MD tau term. Just take the ratio of the two terms, and you'll see that it's GM over R to the 5th. Just on dimensional analysis, okay? And this is B10. And this is 5 p.m. Now it's enhanced by this coefficient to the 4th, because it's actually length to the 4th. I was cheating putting the G here, just to see how it scales with length. It's enhanced by this number. So if a neutron star has a radius, which is, I don't know, 2 to 4 times the Schwarzschild radius, so it's a factor of 2 to the 8 maybe. So this could be, I don't know, 1,000 or something like that, right? Of course, there are numbers in front, but 300 sounds about right. And that's why it's enhanced. And that's why, because it's enhanced, even though it costs you 5 p.m., the good thing that it comes late. So you get the masses first through the shear mass. You get the mass ratio to the first post-Newtonian correction. And then much, much later, towards the very end of the spiral that you can see, you don't see the merger, you try to get this coefficient, and there is a nice enhancement for the neutron star. And then you have models in which you try to cook up what the 5 p.m. relativistic correction will look like, and then you try to read off this lambda. And then you have many templates. Actually, this is not the only one. There are many templates that you can try to cook up, and they all more or less are aligned. And that's how you start learning about, for example, the equation state neutron star. We have not done this analysis yet for the black holes that we observe, because we don't have very long waveforms. And that's what we expect in the future, to have more sensitivity and longer waveforms for higher masses, which are going to merge before they can get to the detector, long and large. So remember, this guy was merging too quickly. The neutron star, has a much longer signal. So we can have something like this now. Then we have a lot more and a lot of signal to noise to do much better, and try to get these numbers. Okay? So that's the goal. That, and also the spin. The spin will also carry very important information. The point is that you need to be very rapidly rotating. And that's not always the case. Although now people believe that maybe some of the detections are actually rapidly rotating, so that could bring some hope that the spin can also tell us about the internal structure. Okay? So I'm going to finish here and give you 5 minutes. And probably I have to finish altogether. Do I? I don't know.
1.
1 what? I have to finish at 1. So I cannot give you 5 minutes. Or I can give you 5 minutes and then finish a quarter after one. Is that feasible? Since I only have 4. Since I only have 4 lectures. Where is Marco? Marco said yes before. Continue? Did you guys want to continue? Yeah, okay. So you're excited or you want to finish faster? Oh, you're hungry, one or two. So one thing I wanted to emphasize now. So we were dealing now with the effective theory of a point-like object coupled to a long-distance field. In this case, the long-distance field is the potential, the binding, and the radiation, but we were dealing mostly with the binding because the disruption comes mostly from the scale R, right? The force of the companion, not from the gravitational wave emission, right? But the same theory will apply to the binary. So what we just found is that this QE term carries a lot of information, the same way as the P dot E term. And this Q can come in 2 flavors. It can come as background field, it's already there, or it can come as a response. I was concentrating now for objects which are symmetric, spherically symmetric in isolation. This is not here. The response knows about tidal effects. Right? Actually, if you're spinning, this knows about spin. And this is for the star. I say star or black hole, right? But the same theory applies now. Oh, I erased it. Also at the scale, there was here, right? Also here, I was saying, we have a theory of potentials plus radiation. We're going to match into a theory of only radiation, and it's always point-like. I was dealing mostly with this theory here, with the matching here, which, by the way, I haven't told you how to match. I haven't told you how to read this coefficient. Well, from the star, you look far away at the field, and then you read off the number. Or you shine gravitational waves to a black hole, and you look at the response, the cross-section, and this operator will contribute to the cross-section, to the scattering, and then just read off what the C is. And I say this because there is some discussion in the literature about whether the black hole has zero love number or not, because when you put a black hole in an external field and read off the metric far away, you have to choose coordinates. And this choice of coordinates can get you confused. Are you computing a gauge invariant object? It's much easier to say, I take the black hole, I compute some cross-section at low frequency, there is a contribution to the scattering amplitude that comes from this guy, omega to the 4. And so it goes like this to the cross-section. So I compute in GR, I compute in my effective theory, I read off its number. Done. So you still need to match, right? But this is part of the whole business. Very good. So, but now this matching here, we can also do here with the exact same theory. With the exact same theory in which now if we're going to do the same, this is for the neutron star or black hole. Now we're going to do it for the binary as a point-like object. Now the difference is that the difference that this E for the neutron star or black hole has the H that has the 2 pieces, right? This could be potential or it could be radiation. And the potential is the one that's doing most of the disruption, right? Because the one that varies on scales which are on length, which are shorter than the radiation. For the binary, we're going to write the same theory, but the coupling will be only radiation because we're going to integrate out the potentials, right? That means that even though the response, in the case of the response of the binary, right, of the neutron star, when we look far away, the deformation, this 300 that I told you, some of that goes inside the response of the quadrupole depends on the internal structure, right? So there are fields, there's all the QCD dynamics, it's very complicated physics. For us, it would be as the case of the neutron star, but only with these potentials that are the ones that we need to care of. Right? Unfortunately, we cannot calculate the matching for the neutron star because it's very complicated. You can do it numerically in QCD and so on. Here we can do it, we just have to solve for these potentials and we have just two bodies. But we're doing the same thing, right? So we're doing the same thing means that we're going to have a background in the short modes, and the short modes now include the potential. And I put it this way because I haven't told you yet what this means. It means that it includes all the bindings, all the short scale physics that the scale R, okay? And a response to a perturbation. But if the binary is isolated, then there is no response. Then plus 0. So it's the same theory, but the interpretation is completely different. In this case, I care a lot about the fact that the star is going to be perturbed by the companion, and that response is going to enter in the waveforms, it's going to teach me about the star. And that's how I'm going to learn about the compact objects. Now I don't want to put the binary in an external field. Why would I do that? What I want is to get the quadrupole in the background. Well, this short means the particles and the potentials, right? Because this is not 0. Because when I open it up and I match, I have a binary that is moving and changing with time, and obviously it has a time-dependent quadrupole. So I just care now about the background value. Okay? So in one case I get a lot about the response or the spin, the background. In the other case I care a lot about the background value because that Q is the Q that entered in the flux. I haven't told you yet how to go from that action to this flux. I'll do that now. But this is what I need. How do I get this? I need to match. The same way that I match for the neutron star. Put in an external field for the neutron star, measure the field, okay? Or I shine gravitational waves, measure the field. I do not do that for the binary because I have much more control over the binary. I know the theory. The neutron star is complicated. But I perturb it and look what happens. The binary I can open up. I can actually do the calculation. How? Well, that contributes to the one-point function as we just determined. So I have a theory of two-point-like objects, and there are some forces between them, and they're producing the long-distance field. Now, this long-distance field is the only one that enters there for the binary. And therefore, I have a theory, I'm getting ahead of myself a little bit, but I have a theory of potentials and radiations coupled to point-like, and here I just have a point-like coupled to radiation. I just go and calculate, what is the one-point function in this theory, what is the one-point function in this theory? I equate the two. Now I have to do a multiple expansion here because this theory is multiple expanded. And when I do the multiple expansion of this theory, which means the spatial variation of this field is much longer than this, which means I Taylor expand the field in multiples, I can read off what the one-point function is here, Hij, and what the one-point function is here, Hij. And then I just read off. This is a theory of Qij's, this is a theory of the full Tij. That depends on the masses and depends on the whole thing, on the masses and the potentials. Computing the full theory, computing the effective theory, do the expansion, which in the other case was the omega r, much, much less than one expansion. In this case, it's expansion of the multiples. It means this wavelength is much longer than this. Do that expansion, keep the lower order term, which is what we did. We kept just the integral of Tij. And that's how we get, for example, the Q. Right? In fact, the leading order doesn't even care about this. The leading order is just the masses, which means you can radiate either from this guy or this guy. So what I'm going to do today, I'm going to tell you in the remaining time how I go from that theory and reproduce this equation. Okay? Then we will do the matching for the one-point function and for the M. If I take the zero vacuum matching without the radiation in the field, so if I look at just the M in the field of the potentials, if I look at this term, without here the long distance field, I get just mdt, nothing else. So if I match now just the vacuum, in both theories, one is just m, the binding energy of the star, and in the other case, what is it? In the other case, is all these potentials between the stars. So I'm going to have a lot of potentials, a lot of binding between the star. This matches into just the m. So I could compute the 1-point function also to match the m, because it will source the background metric. That m of the potential gravitates. So I could compute that 1-point function and get it as well, which means I could attach here long distance gravitons too, and I would get the same answer. But I can make my life much easier just by matching the vacuum amplitude. And that will give me the energy. And I'm not saying anything fancy. You will see how this is calculated, and you will say, aha, now I understand. So by matching vacuum or 1-point function, I can get the m and the flux. I haven't told you how the flux can be computed, but the flux, because I know the q's as a function of the t's, which I know from the full theory. Then I can just reproduce this and I do into all orders. I had to give you the power counting, in which each one of these nonlinear interactions here that I have drawn but not told you yet what they are, they will cost me gm over r, they will cost me v squared. Each one of the multiple expansions that I'm going to do, I'm going to cost me r over lambda, which is also v, and so on and so forth. And then I have to include all these tidal effects that will enter higher orders. So you see there's going to be a mess, but we have clear understanding what we need to do, at which order to include everything. Okay? So what I do now, I will do this carefully tomorrow, okay? But what I will do now is not the matching, but try to go from the effective theory and try to write this, which is what we did, without knowing who Q is. We still don't know who Q is. We haven't done the matching. We know where we're going, but we haven't done it. So let's try to get that equation without doing what we did last time, okay? Let's do it faster. And there are two ways to do it. I'm going to do one way today, and tomorrow, when we do the matching, we'll do the other way. Okay. All right. I'm supposed to stop at 1, but I can take 5 more minutes, right? Okay. If we don't finish, and I'm going too quickly, we take over next time, okay? Please ask me again if you don't follow, because there is no point now. So this is the coupling that we have. By the way, this is just a convention, the half, so that when we match, we get the same Q, okay? So this is a binary that now we treat as a point. And it's emitting long distance, which are the radiation modes, the on-shell radiation modes. These are the on-shell radiation modes. So how we compute now the flux? Well, we can compute an amplitude. Where is the probability to meet a graviton? Okay? Of some given helicity. I mean, in general, you know where this coupling is coming from. So this coupling came from the T mu. So it's essentially, we got it from here in the other way to do things, right? And we computed the 1-point function. So computing the 1-point function is like computing the amplitude. It's the same, right? So if you want to think about it in this way, what happened was, for a given polarization that we're going to meet, this guy will have some polarization, and this is plus or minus. This is proportional to the Tij, and this was the probability to meet gravitons in the direction k, and they are on shell. So this is k. This is what you will write if you write a Feynman diagram. There's a coupling in your action, where it's the amplitude to emit, right? This you treat as a source to emit one graviton, right? That's your amplitude. I'm computing the 1-point function. I'm just using quantum mechanics if you want to compute the amplitude, and square it to compute a probability, and multiply by the energy to compute a flux. But I'm doing everything classically. So what is the probability to meet these gravitons? I integrate over the entire lifetime of the binary. I multiply by the energy. I have a rate, multiply by energy, I get a flux. I will see that this way. Basically, we're reproducing the classical calculation, except that we're doing it in the quantum way, by squaring an amplitude. Okay? Now, what we had before was this projector in the TT gauge. Okay? What's going to happen now is that I'm keeping this ij. Why did I write ij? Because I already know. The only difference is how we're walking into the on-shell technology. We know those are on-shell degrees of freedom. We know the polarization of the two helicity states. We're getting ahead. We're trying to get ahead of ourselves to saying, I don't care if this came from gauge fixing, blah, blah, blah. There are two polarizations, right? And those are the physical ones that are going to come out. And I know how to write this tensor. And the analogous of this lambda ijk that project us into the TT gauge, and the integrals and the multiplications and so on will come because when we square, we're going to have a sum over helicities of the square. So we're going to take this amplitude and we're going to square it. Now, this is the term I'm writing, not this term. So what did I do when I did this? Well, actually what I did was multiple expand this guy, the same way that we did before. But now I'm doing it at the level of the effective theory. So I start already with this guy. So if I start already with this guy, I don't write this. What I write is the Q that is the one. So what I'm doing here is that this is going to have one piece that comes from the Qij, another piece that comes from the octopole, and dot, dot, dot. And something that I didn't tell you because I didn't want to complicate my life is that there is an electric and magnetic. So obviously there is also a magnetic piece. This magnetic piece is like a current. So these Q's is all good, but there is an analogous part which is very important for the currents. So I'm matching the full thing as a multiple expansion in multiples, but I'm doing it at the level of the action. Because the action will give me the Feynman rule for each one of these guys that I can square. But what I did deeply is take this guy and do the expansion that I told you in Fourier space in K. More K's are more derivatives. I haven't told you yet how to include the dot, dot, dot. But how does the dot, dot, dot is going to come out? It's not very complicated to think about it. You just need more derivatives. Because that's what this expansion was telling us. So what can you write here? Well, let's write the octopole. You just have one derivative of this guy. And da, 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 da. And here I think it's an 8. And so on. I'm not doing anything mysterious. I'm just expanding, as I told you earlier, this T in K. Taylor expanding. The first term with the 0 and the omega, if I Fourier transform, is the integral of Tij. And we already show that that integral is two derivatives of the quadrupole. So we're going to derive that directly now. We're not doing this. We're going directly here. But we're basically doing the same thing. But we just expanded the action to read off what those coefficients are, what that amplitude is, and then we square each term individually, which before we did in terms of the expansion. But what did we gain? What we gain is that before, when I did the multiple expansion, I didn't tell you when I squared the stress tensor, when I squared the pseudo tensor, what happens with all those terms? They multiply each other. They're all mixed. They transform as tensors. They are not irreducible representations. It's not when I expand the Tij, remember it was the 0 order, it was an integral of Tij, and then the first correction, that it had derivatives of this guy, and the higher orders, so xi, xj, xk, and so on and so forth. All those multiples. When I square, they all multiply each other. But if I do it this way, they don't interfere. And therefore, I know that each one of them is going to square individually, and all I need to know afterwards is to match and tell you who these Qs are. So I gain a lot by essentially treating the system in terms of multiple moments that don't interfere. So doing your group theory, so to speak. That's the advantage. So now we're just going to look at this term. I'm not going to be doing this, I'm going to be doing this, and then there are two derivatives here, so it's going to be a k square. Okay? So let me write the answer. So here. I feel like I'm going too fast. Right? I'm busy. Yeah. I'm just watching the clock. All right, so let's do the following. I'll do this at the beginning next time. Okay, you guys are very tired. It doesn't make any sense. But I was trying to tell you where we're going, and where it comes from, and what the answer is going to look like. It will be squares. And the lambda projections and integrals that we did before is just this. And if you remember what this is, it's a bunch of deltas and k's and so on. So you plug this polarization sum in your square, and you're going to get the g over phi that we got before doing all this integrals. And now the leftover will be, oh, who the heck are those q's? Okay, and the m, which was the binding energy. So we'll do that calculation tomorrow explicitly, and we'll see if we can, the first correction. We rederive what we did before, hopefully quickly, and then we try to do the first correction. And then, if I have time, I'll tell you what can we learn if we get high accurate waveforms, and where are we going now with these on-shell methods? How are we trying to improve or streamline the calculations? But at least you get the flavor of where this is going, which is the whole point of this. Okay? Thank you.